Welcome back. On the last episode, we were talking about jets and going a little bit more detail on, the challenges that their thermodynamic process, suck, squeeze, bang, blow. We talked a little bit about rotating machinery, and on this sort of second half of that episode, we're going to get into rockets, and then we can kind of complete the jet versus rocket trade. And so I've drawn here the fire triangle again. As a reminder, you have fuel and an oxidizer with some sort of heat spark. And that gives you your chemical energy over to thermal energy and then over to kinetic energy through some nozzle or process. So reminder, in the jet engines, you then took a little bit of that energy to drive your compressor. We're going to talk a little bit about rockets and how this whole thing works as well. But still same process in a rocket, suck, squeeze, bang, blow. And I added here as well just kind of low pressure. Squeeze is where you get to higher pressure. Bang is done at, you're adding heat at high pressure such that now it's hot, and then when you blow, you're going through a nozzle. You're then getting, some of that thermal energy out, but not all. And so I'm going to add here kind of a basic rocket cycle. And really, when we think about rockets, you have to start thinking about the whole process. So, last time I kind of drew just the rocket engine, but we need to talk a little bit about all the rest of it. And so you're starting with that fuel and oxidizer. And so in this picture, and by the way, Everyday Astronaut has some great diagrams and great explanations of a lot of this if you want to go a little bit deeper. In this diagram, you're showing there's a fuel tank and there's an oxidizer tank. Again, remember, back to jet engines versus rockets. Rockets, you're carrying your own oxidizer. And the squeeze process happens with a pump. So you're showing here there's a pump, and in fact, this is a single pump, so single shaft, and it's pumping both the fuel from low pressure to high pressure and the oxygen from low pressure to high pressure. And then those go into the chamber mix that creates your heat. And then the blow here is through the nozzle going to a really high velocity exhaust. And that's where your thrust is coming from. And there are lots of different ways, though, of driving this pump. And so a lot of cycles, different ways of doing it, different pros and cons of each one. This is actually a very simple one where it's called this is kind of open cycle or gas generator, where you're actually going to steal a little bit of this high pressure fuel and a little bit of this high pressure oxygen, and you're going to have a little small reaction that is then driving a turbine and exhausting. So again, just same thing back to the jet engines. The compressor, again here, we would call it a pump in the rocket world. That compression has to be driven by some sort of process. You need energy to drive it. In a jet engine, you're taking a little bit of the energy from the exhaust flow to drive the turbine. Same thing here. But we're actually taking the energy from and kind of doing a side reaction. And so in a separate process, this one's now an oxidizer-rich closed cycle. So what we're going to do here, because if you go back to this, all of this exhaust is now dumping overboard and not really adding to thrust. So there's some portion of this fuel and oxidizer that I'm carrying that I'm not getting to use as thrust. It's just sort of driving my pumps. And so in this version, it's kind of similar, except I want this entire process to happen at really high pressures such that I can still take that exhaust and put it into the rocket engine. Because normally the rocket engines are at pretty high pressure. And so that's called a oxidizer-rich closed cycle, oxidizer-rich because it's actually, all of the oxygen, as you see here, all of the oxygen is going through this path. And you're just taking a little bit of fuel. So the side reaction is now cold oxygen, liquid oxygen, and now you've made it slightly warm and driving over the turbine. So a couple different examples of this, and I'm not going to get all the way into it, but I'm going to kind of stop here and then go into a little bit more on the rocket science side of things. This is the full flow stage combustion where you're doing both. So you have a side reaction for fuel and you have a side reaction for oxygen. So you take a little bit of fuel, go into the oxygen, take a little bit of oxygen, go into the fuel. And this is what SpaceX has done with their new Raptor engine. So pretty advanced. This sort of represents the most advanced. But I want to get into some of the math to show you why this works, and ultimately then getting into kind of the full performance envelope of a rocket, and then we'll finish talking about rocket-based combined cycle. And so just to start off with, I'm going to go back to just F equals ma, and so ma equals thrust minus drag, and then I'm going to go ahead and put gravity here, any kind of gravity force. And so because we're talking about rockets, what we want to do is sort of just approximate this at the very beginning and say, what, the rocket is I'm trying to go to orbit. The rocket is not going to be in the atmosphere too much. So I'm going to ignore this. And then really, one of the first things you need to understand is that space is actually going sideways fast. And so, what you're really trying to do is get up out of the atmosphere, but ultimately it's Mach 25 or 5 miles a second, 8 kilometers per second sideways in order to stay kind of circular around the Earth. And so, from that point of view, yes, you're going up. That the potential energy rise is also pretty insignificant compared to getting all the way up to that kind of speed. And so, for the most part, we would just kind of ignore this, right? And so, from this point of view, then, if I go back to my what's making the thrust, well, I have some sort of mass flow rate of the engine. It's going to be important here a second. Time the velocity of the engine. Now, there may be a pressure term. I'm going to get into pressure terms here in a second, but for right now, we're just going to do a basic derivation of the rocket equation. And then acceleration is actually the time rate of change to velocity with respect to time. And if you haven't seen this dot before, this actually just also means time rate of change. Now, the mass flow rate into the engine, this is the mass of the rocket. And so I actually need to do one more conversion, which the mass flow rate of the engine is the same as the opposite mass flow rate of the rocket. So this is actually negative m dot. And then my exhaust velocity, I'm going to use the specific impulse term instead. And so that's a really specific impulse, and then we have to multiply that by gravity for units point of view. And I'm going to bring this mass to the bottom, such that this is now the equation of time rate of change of velocity. And so if you then integrate to this, you get the famous rocket equation. And so this mass is changing, right? Your rocket is actually getting lighter with time, right? You were draining the tanks. So this mass is not constant. And so when you integrate, it's where you end up getting a natural log. And so in the end, this is then, we would say delta V, so the final velocity minus initial velocity, delta V, is equal to ISP. We'll assume it's constant. It's not. We'll get into that in a little bit. ISP G, and then natural log, and you end up having sort of my initial mass over my final mass. Or writing this, many different ways of writing this equation, but I'm going to kind of finish it here. ISP G natural log 1 over 1 minus lambda. Now this is the kind of the packing fraction. How well, lambda is propellant, total mass. So there's a sort of an upper limit. Rockets, usually the entire stack is about 90% liquid. And that's what it takes. That's not much left over for structures and engines and, the payload thing you're trying to do. So this is the rocket equation. And we will use this here a little bit later to kind of evaluate some of the rocket engines. And then, this will kind of plant the seed for detonation engines and why, hey, this ISP term, making it go up with detonations is a pretty big deal. But I really want to spend some time on kind of the full term here a little bit, so we know that we have to kind of look at this whole equation, and it's not fair to just look at ISP because there are some choices a little bit different. But first, just a little bit more on kind of rockets and space and things like that. Also, people don't always understand just how busy space is. And so you can see here, this is kind of a picture of all the satellites in low Earth orbit. This is kind of the picture of geostationary orbit. So it's getting busier for sure. And here's another fun one to kind of adjust yourself. But the moon is really far. So this picture is actually to scale, right? And here's the Earth, right? The diameter of the Earth. The moon is like 30 diameters away. It's way over there. In fact, geostationary orbit is about 3.3 Earth diameters. And then this is unclassified, but we sort of have hard time seeing things past that. There's some interesting use cases as we're thinking about cislunar applications. So the moon is really, really far. So be impressed when our friends over at Intuitive Machines and other people making the attempt to go land. That's a really far away. And then be impressed as well. Spaceship is one, it's a monstrous rocket, but not only it's the new engine of the Raptor engines, the cost of launch honestly is coming way down. Falcon 9 and reuse of Falcon 9 is dropping the cost to get into orbit, and Starship will do even more of that. So even from a economy point of view and markets point of view, there are a ton of applications coming that can happen in space that are pretty exciting because of the cost reduction. So all of that works, though, but you have to take account that propellant density. So this is how much propellant I'm carrying by mass. And so when you look at ISP, so this is a graph here of ISP and then propellant density, and a couple different things that are really interesting. So your propellant choice really matters. The highest specific impulse engine from a rocket point of view, humanity has made is actually a liquid hydrogen, liquid oxygen engine. This is what we had on the space shuttle. And while it's really high ISP, hydrogen, compared to the density of water, hydrogen is actually 0.07 in its liquid form, like cryogenic, really cold liquid form. And so it doesn't pack very well. And so the combination of your total propellant density with the oxygen you're carrying and that hydrogen, which would be the red stuff over here in this case for the space shuttle or other launchers using liquid oxygen hydrogen, you don't really pack that well. You end up having a lot of structure. Or think of the space shuttle. All of the performance of that engine was effectively eaten away by how big that big orange tank was. And so when you do the final curve of sort of payload to orbit, which would be how much of this term in the leftover structure, right? If this is how much propellant my payload is usually around 2%, you can kind of see here why, hey, it's not quite obvious at first principles which is better, liquid hydrogen engines, or the more classic liquid oxygen RP, which is just kerosene. And then I've also plotted their methane. You're seeing companies now go into kind of liquid oxygen methane. It is actually a slight bump up in performance, particularly if, like SpaceX, you're able to kind of go back and do the full stage combustion. But it's kind of splitting needles. Some of the excitement of it, though, is it burns a little bit cleaner. And so when you're driving your turbopumps, it burns a little bit cleaner. But also, if you're going to go land on Mars, you can actually extract methane from the atmosphere. And methane is cheap, right? Natural gas is pretty cheap. So there are reasons that you're seeing SpaceX and Blue Origin and other companies switch kind of over to a methane-based propulsion system. And I want to highlight here, though, and we'll dive into detonation engines on a later episode, but we've already kind of talked about detonation engines to a kind of broad stroke. And so these two diamonds on this plot represent what a detonation engine would do. And so the first one, Venus, we've been doing some work with NASA on LOX methane detonation engines. This would represent if you were using detonation engines on both a boost and a kind of second stage point of view, that the amount of payload will go from that 2% up to this 8%. So that's pretty awesome. You're talking about a quadruple, potentially, if we can achieve all that performance out of the detonation engine. This is a quadrupling of what you're seeing getting into orbit. And then the other diamond I have here is because here at Venus, we are using hydrogen peroxide. When I get into the hypersonic deep dive next time, I'll go a little bit more why. This drag term you can't ignore is kind of where it is. So the mass fraction, how much you're packing into the vehicle in a hypersonic flight condition is actually really important. But I wanted to just highlight here, usually a hydrogen peroxide RP would be below this from a detonation engine point of view. It's not, or sorry, from a deflagration point of view. It's really not a great orbital rocket combination. It would be a little bit lower than LOX RP, but then with detonations, it brings it up. And it's certainly, liquid peroxide is a lot more dense than water. So again, on average, it's about 1.15 combined density. So I want to talk now a little bit about nozzles. And so down here at the bottom right, this is your nozzle. So when you think through the performance, so here we've just generically said ISP, but where is it coming from? Some of it is that chemical reaction. So right, how much energy are you getting out from the chemical point of view? Are you able to combust it really well? So different injection patterns will matter. If you're doing a pencil or a shower head, like all of these will matter in terms of how well you're actually getting that chemical to thermal conversion. But then this final conversion of thermal to kinetic, it's through the nozzle. And so this is a really kind of detailed portion of it. But in the end, the graph you want to take a look at kind of looks like this. And it's a CF, and this is kind of, in the end, it's how well is my nozzle doing. Basically, we end up saying that we're going to take the thrust. I'll write it here. We're going to say the thrust is just choosing a number, or this is the pressure inside the chamber times the area of the throat times CF. So we just want to see how well, for the same pressure of the same throat area down here, the same throat area, how well do all of these different nozzles compare? And so if you are able to expand perfectly, that's the optimal one there in the bottom, you would right along a curve, something like that. That would be your optimal condition. And the bottom axis, this is all right altitude, but you can also think of this as pressure ratio between the pressure in the chamber versus exit pressure. And so now I'm going to draw a couple different curves on here. And so this would be if you had an optimal expansion, if you could somehow make your bell nozzle the perfect exact thing, but it doesn't happen. So look at this graph on the bottom right. Here it's overexpanded. And so this would be lower in the atmosphere where the pressure is high. It's actually squeezing that plume. So it doesn't get all the way out. And there's some inefficiencies there because of how the flow is not straight. And then that same bell nozzle at higher altitudes is now overexpanded. Again, it's not perfect. It's kind of shooting out sideways. You're getting some losses. And so what ends up happening, you end up having a curve that looks a little bit like this. And so a single nozzle may do something like that. This might be, say, an area ratio of 10 to 1. That would be the area of the nozzle compared to the area of the throat. And then you may have another engine choice that may do something like that. And that might be like, say, 300 to 1. And so what rockets will end up doing, because rockets actually is really a rocket carrying a satellite. So a rocket will launch, this is the boost phase, and it'll get up to around Mach 10, maybe Mach 12 on some conditions. And that first stage engine will shut down, the rocket will split, and then you'll have that smaller rocket lighting a different engine carrying on. And so that second stage engine is usually a much higher bell because you're starting at much higher altitudes. And then the boost engine, right, that stage 1 is usually a lower, such that you're getting good performance at kind of sea level, and then you're able to go in. So there is a design called an aerospike, and that's what you're seeing here. An aerospike, where you kind of invert it, you basically have a ring of fire, and this will be interesting for detonation engines, right? Where you have a ring of fire, maybe it's multiple combustors, but you're driving a ring of fire along kind of this aerospike. And so as the pressure changes in the atmosphere, you have optimal straight flow at sort of sea level, the design altitude, and then even off into space. And this is a diagram from Pangea Aerospace, who's chasing aerospikes. And so that would let you ride this curve. Now, one of the challenges with aerospikes, one of the reasons you haven't seen people do it, is it's a little unclear what the performance is ultimately going to do. So we know we can do the math on the performance, right? And so again, looking at the payload chart, an aerospike might take my payload from, say, 2%, and it might go up to, say, 4%, right? I can do the math, I can do the integration. I'm estimating, oh, wow, look at all this extra performance. The challenge has always been that this is a heavier engine as well. And so if, engine might normally be, say, 2% of the mass of the vehicle, and if I just double the weight of my engine, then it's actually not up to 4%. I need to now subtract off the extra mass of that engine. And so you're sort of left with something that might be 2%. So this has always kind of been the challenge of many different companies that have taken a look at it and kind of been impressed by aerospikes. It's always this, like, in the end, once your system is fully built, are how much is actually your performance going to be? We know the theoretical goes up to 4%, but is the mass of your system has always kind of been the challenge. And so that's why you haven't really seen aerospikes, because it's sort of an unknown final mass challenge. Okay, so the last thing I want to talk about a little bit here is then rocket-based combined cycle. So in applications of hypersonic, we're talking about you need some system to get you from Mach 0 up to Mach, whether it's 3, 3.5, in order to start that ramjet. And so rocket-based combined cycles, what you're trying to use is a rocket engine. This is a great graph where I have a rocket engine drawing the air in instead of reducting it. And this suction, and we use this a lot in the Navy as well, right, to kind of pull out things with a high-pressure pump where you're ducting it. It's going to draw the air, and it's going to mix it. So you're going to get, it's going to warm it up and mix it. And then once it's fully mixed, you normally get a shock wave here. And then what you have here past this is sort of high-pressure, high temperature. And so you can link a ramjet downstream of this, and you can actually establish ram start really early. Now, the challenge in all this has always been that ejector core flow length, highlighted there in red. And so, take a look at this, SpaceX Falcon 9 launch, and just look how long that plume is. That gives you an idea of just how long a column of fire, right? If you're using a rocket engine like below, how long that column of fire is mixing with the air. So, right, I made sure you could see the launch pad here. This is sea level. and how long it takes to kind of mix with the air before you can't see it. So rocket-based combined cycle is an old idea, and it kind of stalled out in the mid-2000s because of this, right? The length of mixing duct that you needed in order to do this was really long. And so that had mass challenges, it had thermal challenges, and then as we'll kind of cover in the hypersonic section, the volume of your vehicle, the drag goes like the volume squared. And so if you're adding volume just as mixing length, it's going to hit that drag penalty and be pretty rough. And so this is where detonation engines are pretty exciting because we don't have a column of fire, we have a ring of fire. And so just from a surface area point of view, this is now going to increase the surface area with the air, and it's an unsteady ring of fire. And this is part of the experiments that Venus did in the fall, where we took our detonation engine and we mixed with air. And we actually took that length, that mixing length, down by a factor of 3, which is why now we're really, really excited about using the detonation engine in this capacity. And so that's kind of want to talk about rocket engines and kind of finish there. So we talked about, again, it's the same kind of combustion, chemical energy to thermal energy to kinetic energy. We do it through a nozzle going into, a combustion engine going into a nozzle. We've talked about, what is the rocket equation, where that delta V, your change in speed as your vehicle, is related to the performance of your engine, but also that mass fraction. Showed you some curves that looked at different propellant combinations because that mass fraction does make a difference. And then we talked a little bit about nozzles and nozzle choices, aerospikes, and then kind of finished here with a little bit on the rocket-based combined cycle of the challenge has always been mixing length, and that's really what the detonation engine solves. So stick with us next time. We'll talk about the hypersonics and then get into more details on the RDRE. Thanks.